All right, hello everybody. Welcome back to Statistics for Linguists. We're here outside again on Thursday, November 25th. It is actually American Thanksgiving, and here in Calgary, Alberta, it is over 10 degrees Celsius today. I think it's like 52 Fahrenheit, 11 degrees Celsius. So I'm still going to record outside because you got to take advantage of these moments when they come. And who knows, because of global warming, we may get them forever for the rest of our lives. But either way, it's really nice right now. And today we're kind of talk about improbable things and how we measure like how likely or probable they might be, because we're going to get into binomial distributions. And as sort of an entree into that discussion, I want to show you this clip from this movie called Rosencrantz and Guildenstern Are Dead, which you may have seen or heard of from wherever, but it stars, it's about these two very obscure characters from the Shakespearean play Hamlet, Rosencrantz and Guildenstern, who just have a very minor role in that play, but in this movie they're the central characters. And this is the way the movie opens up. It stars Tim Roth and Gary Oldman, who are two British actors that you might be familiar with, especially if, like me, you grew up in the 90s. And here they are, wearing masks even before the time of COVID. It's funny, I once watched an episode of Jay Leno where he was interviewing Tim Roth, and he said, "Oh, because you've been in Planet of the Apes 2, now you've made it." And it's like, I think Tim Roth made it long before that ever happened. I guess it serves me right for watching Jay Leno, though. Anyways, something's about to happen.
Whoa. Heads. 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 Heads.
Okay, I think we can stop it there because you kind of get the idea. That actually goes on for quite a while in this movie. This is known as theater of the absurd, or I guess cinema of the absurd, because things don't entirely make sense, and that's just the way the movie opens to kind of let you know that Rosencrantz and Guildenstern are making their way into a world which doesn't make a whole lot of sense, I guess, or maybe is over-predicted, you might say. So hopefully that clip will get past the YouTube censors, and if it doesn't, I'll just say that in this little clip of Rosencrantz and Guildenstern Are Dead, Gary Oldman, I can't remember which character he plays, flips a coin and it keeps coming up heads over and over and over again. Okay, so anyways, if you get a chance to watch that movie, watch it, but it's a little weird. So if you like weird things, go ahead and enjoy it. If you don't say I didn't warn you. Anyways, last time we learned about a couple of different principles of probability. One was the sum rule, which we can apply to mutually exclusive events. The other was the product rule, which we can apply to independent events in calculating their joint probability. And then at the end of the discussion, we talked about the choose function and how that works. And we're going to kind of build on these as we go here. But like I said at the beginning of this lecture, we want to talk about binomial distribution specifically in this particular lecture. We also played a couple games of pseudo Dungeons and Dragons and also pseudo Scrabble, but thankfully nobody was injured. So we don't have to worry about that anymore. But we will play a little more Scrabble in this lecture, again, to kind of think of how probability might sort of tie into sort of more linguistic-y structures like words or syllables or that sort of thing. Okay, so third game's a charm. This is our third little Scrabble game, and in this game, again, I'm going to do it just with a random number generator using a Perl script on my computer because I don't have the tiles with me. But in the real version of the game, what I would do is I put 10 tiles in a bag. 5 of those tiles would be vowels, and then 5 of those tiles would be consonants. 5 vowels, 5 consonants, and then I would walk around the classroom and hand the bag to 5 different people. Each person would pick out 1 tile out of the bag, tell us whether it's consonant or a vowel. Then I would write that down on the board, and then they would put that tile back in the bag, and I'd hand the bag to a new person, and we'd repeat the process over and over again. And what I want to do, I'm going to do this quite quickly using a computer program, but I'm going to repeat that process 5 times. And so there will be individual consonants and vowels that will come out of the bag, and we'll be able to report what those are, but we're going to kind of identify them as either consonants or vowels. So this would be like, forming little syllables, like CV syllables in a language, perhaps. Yeah, it's funny. In doing this, I just set it up with sort of the 5 vowels and then 5 really common coronal or alveolar consonants in the English language, and it turns out those are just the 10 tiles in Scrabble that have a point value of 1 only. And so I think the vowels are the vowels, and I think the consonants are T, S, and L, R. So take that for whatever it's worth. Those are the tiles you are not excited about getting. If you are playing a game of Scrabble, let's see what we get when we play this little inane game. Yeah, so Scrabble game number 3. Hopefully this is big enough for you to see it. We're going to pick 5 tiles out of the bag, and we get S-I-A-E-U. That's a sequence of C, V, 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 V. Yeah, okay, for whatever that's worth. Just to show you, this is random. I can do this multiple times. Usne is V, C, C, V, V. Yeah, T-A-L-A-O. Right, so on and so forth. C, V, C, V, V. Right, so why am I doing this? It's not because I'm a monkey banging on a keyboard trying to recreate Shakespeare, although I might do that later. But I want to ask, what is the probability of getting these strings of consonants and vowels? So for instance, what is the probability that we will get a 5-letter string with no vowels? And I think this is a question that you can answer. Remember, we have 5 consonants and 5 vowels in the bag, and we just pick randomly and then replace after we pick, and we make those choices 5 times. So I think you already know the principles you need to know to answer this question, so I'll just take a little drink while you think about the answer. And we can also answer, once you figure out the answer to that one, what about the probability of getting 1 vowel or 2 vowels, and so on and so forth. So to begin with, what is the probability of getting any particular 5-letter string, like say CV, CVV, or something like that? Well, for each selection, the probability of getting a C is 1 out of 2 because there's evenly balanced numbers of consonants and vowels, or the probability of getting a V is also 1 out of 2, right? So for that, you simply just multiply that probability 1 out of 2 5 times. You're using the product rule there, right? Because those are each independent events, and the probability of each one of those things happening is 1 out of 2. So for any particular 5-letter string, the overall probability of getting that particular 5-letter string is going to be 1 out of 32. That's 1/2 to the 5th power. The next thing we have to worry about, though, is how many different 5-letter strings containing vowels, 0 vowels, are there. So we've already kind of answered these initial questions, but then you can think, once we start getting some variety in the different strings in terms of like C's and V's, that we can get different types of 5-letter strings. So you can have, say, well, with 0 vowels, there's only one of those possible strings, right? C, 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 C. But when you think about like how many different strings are there with 1 vowel in them, you could have the vowel in the first selection, like V, C, 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 or it could be in the second selection, like C, V, C, 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 so on and so forth. And if you start to think about it, there's 5 different slots where that vowel can fit in. So there would be 5 different possible strings containing just 1 vowel. So for the answer for 0 vowels, just 1. The answer for 1 vowel is 5. And there's actually another way you can actually go about answering these questions aside from thinking about it. With these numbers, it's relatively easy to kind of reason through the number of possibilities, but you can actually use the choose function to help you out here if you don't want to have to do all that conceptual work on your own. So when we have a 5-letter string with 0 vowels, it's sort of like we're choosing 0 out of 5, so we can use the choose function and just say 5 choose 0. It turns out that's equal to 1. And I should explain how this one works because it uses a value of 0 factorial, which we haven't seen before. But it would basically just be 5 factorial divided by 0 factorial times 5 factorial. And 0 factorial is just defined to be 1. 1 factorial is 1 and 0 factorial is 1. So they, just kind of don't get involved in this equation in any meaningful way. And we just wind up with 5 factorial divided by 5 factorial. And that's going to be equal to 1. The wind's kicking up here a little bit, maybe also a little improbably, but hopefully it's not going to ruin the audio to this too much. I'm just going to keep on rolling through it, and I'll check it later. So here's how the other string possibilities shake out, and we reasoned through this one with a 5-letter string, and you can have a vowel in each sort of slot in the selection sequence. You can get 5 different possibilities. With 5 choose 2, the value is equal to 10, and I think you can reason through that as well. So if you have 2 vowels, let's say you have a vowel in the first slot, then there's 4 other options where the other vowel can go, so that's 4 to begin with. And then if your first vowel is in the second slot, there's 3 other places the vowel can go, so that's a total of 7, right? 4 plus 3. Then if it's in the third slot, there's 2 other options, that's plus 2, and then plus 1 at the end. That winds up being 10 total. As we go down kind of the higher numbers of vowels here, it just kind of works out the same way, both in terms of the choose function and also conceptually. But you can kind of think in these terms instead of choosing 2 vowels, because we have 3 here, you can think about choosing like 2 consonants and where can they fit in to this 5-letter string sequence. And then here, just 1 consonant, where can that fit in the sequence? And at the end, it's no consonants, right? So we wind up getting this nicely symmetric pattern where we have 1 possible string for 5 choose 0, 5, 10, 10, 5, 1 as we go all the way through the different distribution, the whole distribution. So our probability distribution is going to therefore be for 0 vowels. There's only one way that can work out in terms of the sequence of C's and V's. The overall probability of picking that particular sequence of C's and V's is 1 out of 32. So 1 times 1 out of 32 goes 1 over 32. That's the likelihood of getting that result. I didn't count when Gary Oldman was flipping his coin, but it's probably at least 10 times that he did that. It winds up being a lot more than 10 times in the actual movie. But you can already see how that would be extremely unlikely because the probability of getting heads or tails in any coin flip should be 1 out of 2, right? Anyways, moving right along for the C's and V's, not thinking about coins at the moment, we have 5 different possible 1-vowel strings. Each one of those has a probability of 1 out of 32, but those are mutually exclusive events, right? So like the likelihood of getting V, C, 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 C is distinct or mutually exclusive from getting C, V, C, 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 right? And so on and so forth as we add up all of those individual strings, the probabilities of those individual strings. So we add them up because we're using the sum rule here. And we, as a shorthand for adding, we just kind of multiply them by the number of possible CV strings with 1 vowel in them. So we get 5 times 1 out of 32 equals 5 over 32. For 2 vowels, we get 10 times 1 out of 32, and hopefully you can see where this is going. So for 3, we get 10 over 32 as well, and then going down the backside, we see this is symmetrical. So for 4 vowels, it's 5 out of 32. For 5 vowels, it's 1 out of 32 as well. Okay, so like I said, that's nicely symmetrical, but there's kind of 2 factors going into it. One is calculating the probability of that particular string happening, and then the other is kind of counting how many different strings you can get with that number of consonants and vowels in them. Okay, so this is what that distribution would look like if we plotted it out with the number of vowels here on the x-axis and the here on the y-axis. And as you can see, it's nicely symmetrical, so we don't need to say a whole lot more about it than that. And in the next game, though, I want to complicate things a bit further by putting 5 more consonant tiles in the bag. And in this game, we're going to do it the same way. Normally, I would just walk around the room and have 5 different people pick one tile out of the bag and then put it back in. But in this case, the overall balance is shifting a little bit because people will be picking tiles out of a collection of 5 vowels and 10 consonants. So what we want to figure out, based on the principles we've just learned, is how would this change the overall probability distribution. I'm going to actually pause right here for a moment and see if this wind that's moving, this Zephyr wind or Chinook wind that we're getting, is actually getting into the microphone, so I don't want to create a bad video for you guys. And if it is, I'm going to move over to the car. And with that in mind, I'll just show you our nice little Chinook arch. Hopefully you can see that. It's a beautiful day with beautiful clouds here in Calgary, Alberta. But for now, I'm going to sign out. All right, hello again, everybody. I just listened to the previous video I made, and I want to say I apologize for the wind blowing in the microphone. That was not great. I'm not going to edit it out because I don't think much was lost on the basis of that alone. It just got kind of really annoying. But I think it was clear enough if you watched all the way through that what we're going to do next is pick consonants and vowels out of a collection of 5 vowels and 10 consonants. And again, we're going to be replacing the tiles that we select each time we select them. I can just give you a quick example here of how this would work. So in this one, I think what I added, in addition to those 5 mostly alveolar consonants of T, S, and LR to the vowels, I think I also added D and G because those are the 2 pointers in Scrabble, and then also B, M, P, which are 3 pointers. And wow, it's really kicking up here, even now that I'm in the car. Anyways, so we have 10 consonants, 5 vowels. Let's pick 5 of them. What do we get? We get a sequence of V, C, 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 V. Isnry is the sequence of particular tiles. And like I said, I'm just doing this at random. A, E, T, L, I, V, V, C, C, V, that sort of thing, right? Okay, so what we want to figure out is how this would change the probability distribution that we've plotted here. In terms of what is the probability we'll get these numbers of vowels out of selecting 5 tiles out of this bag, so from 0 to 5. Okay, so the first thing which you should recognize, or I should tell you, in calculating this probability, is that the number of different 5-letter strings containing 0 vowels, 1 vowel, 2 vowels, etc. will not change. And this particular set of numbers is calculated by what is known as the binomial coefficient. And just to go back to what I mean by this, that's this particular sequence, which is based on the choose function here. So there's only one string which has no vowels in it, and then correspondingly there's 5 strings which have 1 vowel in them, 10 strings which have 2 vowels, so on and so forth. These numbers going from 1, 5, 10, 10 to 5, 1, that's the binomial coefficient, and that's not going to change. But what will change in our new calculation is this bit here, if I can get it. So before, we were just saying the likelihood of getting any one particular 5-letter string is 1 out of 32. We calculated that here with the product rule. That's going to change, right? So before, what we said is that we have 5 vowels, we have 5 consonants, we're just picking one letter out of the bag. The likelihood of getting either a consonant, a vowel in that case is 1 out of 2 for both options. But that's no longer the case, right? So now we have 5 vowels, 10 consonants, so the overall probabilities change, right? Hopefully you can see there's 15 total tiles in the bag. 10 of them are consonants, so the likelihood of grabbing a consonant out of that bag is 2 out of 3. And the likelihood of grabbing a vowel out of that bag is 1 out of 3. And we have to factor that into this part of the overall distribution equation. Okay, how are we going to do that? And I've got this note here, is what changes is the probability of getting any particular 5-letter string. So what's the probability of getting a 5-letter string with 0 vowels? There's only one string which has 0 vowels. It has 5 consonants in it. So that means each one of those consonant selections is an independent event. We calculate the overall probability by using the product rule. So that's going to be 2 out of 3 times 2 out of 3, so on and so forth, 5 times 2 out of 3 to the 5th power winds up being 32 out of 243. Okay, so that's how I calculate the probability of getting that particular 5-letter string with 0 vowels. How would I do it if I had 1 vowel in it? And here we don't have to worry about where in particular we find that vowel in the string. We've kind of already taken that into account by saying, well, there are 5 different possible strings which can have 1 vowel in them. What we want to know here is just what's the probability of getting any 5-letter string with 1 vowel in it. Each selection is an independent event. The probability of getting that vowel is 1 out of 3. The probability of getting a consonant is 2 out of 3, but the consonant selection happens 4 times. The vowel selection happens once. So the overall probability, again, we're using the product rule here, but we're getting 1/3 for the vowel selection. And then we're multiplying that by 2/3 4 times. So 2/3 to the 4th power. And that just winds up being 1/3 times 16 over 81, or 16 over 243 in total. Okay, before we have 32 out of 243, you might already get the sense that our overall probabilities are probably going to go down as we do this. And you'd be right if that's the case, because it's less likely that we'll get a vowel selection out of this than a consonant selection, but we can just keep doing the math the same way, right? So before we have just this 1 vowel slot with a probability of 1 out of 3, we'll just keep moving by replacing this consonant with a vowel and just keep doing the same math with the product rule. So this is 1 out of 3 times 1 out of 3. That's 1/3 to the 2nd power times 2 out of 3 to the 3rd power. That equals 1 over 9 times 8 over 27. We get an overall probability of 8 over 243. Maybe if you're really good, you might also get the sense that this number on the top of the fraction is going down by a factor of 2 each time. And if you see that, it kind of makes this a lot easier to contend with in this particular case. So we're going from 32 on the top to 16 to 8. You might guess the next one will be 4, and you'd be right. That just happenstance of this particular setup. That's not just a general principle of how this works. The general principle of how this works is more involved with these probabilities and the powers we take them to in the middle here, because that's how we're going to kind of formally express this when we get to the end of this process. But we can just keep going. We got 2 more options left. For 4 vowels, we get a total of 2 out of 243. And for 5 vowels, we get 1 over 3 to the 5th power, because we're selecting 5 vowels only, no consonants. And that gives us 1 out of 243. Okay, that's enough numbers for now. We can take a look at this and say that our probability distribution overall should look like this, where with 0 vowels, we get a probability of 32 over 243. And then for 1 vowel, we've calculated the probability of getting a particular 1 vowel sequence as 16 over 243. But again, remember we have 5 different such sequences. And they're mutually exclusive, right? So we're adding them up basically. And that means our probability for 1 vowel overall is 5 times 16 over 243, or 80 over 243. Okay, so do the same thing for the 2 vowel sequences. Multiply this probability we just calculated of 8 over 243 times 10, and we get, again, 80 over 243, so on and so forth. For 3 vowels, we get 10 times 4 over 243 equals 40 over 243, and the last 2 options are 10 over 243 and then also 1 over 243. So we're calculating these probabilities of getting any individual string that has these particular numbers of vowels in them, and then we count how many different strings could have that number of vowels in them, and we multiply them together because those are mutually exclusive events. The main point, though, is that this is what our distribution is going to look like. It's not symmetric anymore, and it's not also centered anymore in the middle of the possible distributions. It's skewed a little bit over here to the right. And, like this bump here for number 3 is a little bit bigger than a bump for number 1, even though 1 and 2 are the same. But if you add all these numbers up, 80 plus 80 plus 40 plus 32 plus 10 over 1, and so on and so forth, you will get 243. So the whole thing will add up to 243 over 243, or 1. These are all the possibilities out there for us with this setup. Okay, that's a lot of number crunching, and I apologize if you hate thinking about numbers that much, but I wanted to make it explicit where this is all coming from, because I think you can figure this out intuitively. And doing so is more helpful than just telling you that this is what is called the binomial theorem, even though this is the result of using what is called the binomial theorem. Okay, and if you don't believe that doing this sort of number crunching stuff was easier than just looking at the binomial theorem, I'll test you by showing you this next slide. And this is what the binomial theorem says explicitly. It says that the probability of observing k hits on n trials when the probability of observing k on any given individual trials p is n choose k times p to the k power times 1 minus p to the n minus k power. This is exactly what we've been doing, hopefully relatively intuitively, but this is how you generate that sort of binomial distribution that we just saw a second ago. So this is kind of the part that tells us how many particular strings we have with k hits in them. And then if the probability of getting a k hit is p, or the probability of getting a hit is p, we just multiply that by or take that to the kth power for k hits. And then this is the probability of not getting hit, 1 minus p, and we take that to the n minus kth power, which is the number of times we don't get a hit on any individual trial in this sequence. Like I said, that's a lot of words, and it's kind of easier, I think, to see it in the math, but it winds up taking us to the same place. And this is the binomial theorem. It's just basically a way to generate one of these distributions. I think I'll pause here for a second and say, if you remember, way back at the beginning, I talked a little bit about the math behind the normal distribution or the Gaussian distribution, because Carl Gauss was the guy who figured out how that math worked. We haven't thought much at all about the math behind the distributions ever since, but this is one case where you can kind of relatively easily understand how the math works behind generating one of these distributions. And beyond that, once we get a distribution shape, sort of hypothesis testing paradigm we're going to plop down onto it will work basically the same way. We're just getting a slightly different distribution shape from what we've seen before. So the plot of probabilities generated according to this equation is going to be called the binomial distribution, right? And it can vary with the different probabilities you might get in your sort of setup here, and also with the different number of hits, which are represented with k out of n here, where n still remains the number of items in your sample. Okay, so that's theoretical, and maybe it's clear by now, or maybe it's not. Hopefully, if it's not clear, I can make it a little more clear for you by walking you through how this works in R with specific examples. And I'll start with the choose function, which I played around with a little bit last time. Maybe I'll put this up here. We saw this before in the previous lecture, and we also kind of saw it again when we were calculating how many different kind of strings or options we can get for numbers of vowels in, didn't want to do that at all, in our 5-letter sequence of consonants and vowels. But 5 choose 3 is 10, right? And you can figure that out using the factorial math too if you want. Another way you can do this in R, sort of shorthanded way, is instead of picking a particular number, so this is 5 choose 3. This here says, give me what the values of 5 choose 0 are with, go through the whole sequence for choosing 0 to 5 by putting this sort of 0:5 notation on this side of the command. And if I do this, just hit return, it gives me that whole sequence that I saw just a second ago, right? 1, 5, 10, 10, 5, 1. So I do a whole set here rather than just one at a time, which is nice. And obviously it doesn't take R long to figure that out. So again, use the computer's speed to your advantage. We can also plot these by just dumping them into a vector, which I'm going to call number of outcomes, if I can figure out how to type in my car. And I used to plot these out with just the regular sort of scatter plot command, which I think you can see relatively well, but I learned this on this go around that it looks a lot better as a bar plot. So I'll plot them out that way, and we've seen these kind of already. This looks more like sort of a regular histogram or distribution that we might plot out in class. I'll just point out here, we haven't seen this bar plot command before. So it just says plot this, the values of these, right, which we see up here. And then this names.arg part is what's going on the x-axis, basically telling you what to label the x-axis with. And this just says go from 0 to 5 on that x-axis. And then on the y-axis, I'm plotting out 1, 5, 10, 10, 5, 1, right? Yeah, that's super convenient and simple. So use that only for good, never evil, as usual. Let's try something else here. I want to calculate a probability distribution for kind of the first setup we were playing around with today. So where you have a 1 out of 2 chance of selecting either a consonant or a vowel. This is our first Scrabble game for today. We can plot the overall probability of selecting an individual string of C's and V's that way into this P value here, which is equal to 1 out of 32, or 0.5 to the 5th power. So I'll dump this into a new binomial distribution where P remains constant. And then I've got this binomial coefficient, which is where I'm selecting any number from 0 to 5 from 5. And we'll take a look at that particular sequence of values. We've actually seen them before because I showed you this plot, and I'll plot it again in a bar plot. But this is how you can easily generate that first set of values, which took us a fair amount of time to kind of walk our way through. And there was a lot of wind involved too, is that part of the lecture. But it looks like this, right? We've seen that before right here on slide number 6. Okay, that's how you generate that in a few simple commands. What I want to do, well, first of all, I'll show you that the overall sum of this is equal to 5. So like this is a vector of numbers, right? There's 6 different numbers in here, but I can sum the whole thing just like this. And I think I said the sum of this is 5, which I shouldn't have said because the sum of this is 1. Basically, that equals 100%. All of the different options are in there. So hopefully I didn't misspeak there. But what I want to do is to try this with 40 trials rather than 5. And then ask, how do you think the distribution would change? So this would be like if we're choosing, if we're going back to our bag of 5 consonants and 5 vowels, and we select a tile and then replace it, and then each person in class does it, but we walk around to 40 different people, and they each select a particular tile. Maybe we can do that this way, just to see what an example would look like. Yeah, so here I have 40 different tiles that I've selected. It doesn't fit on the entire screen. But, you know, a lot of vowels and T's and R's and so on and so forth. So the whole sequence is V, C, C, V, 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 so on and so forth. Okay, let's think about that sort of situation. The probability of getting any one particular sequence, like the one I just got, would be 0.5 to the 40th power, which is a very small number. It's 9.09 times 10 to the negative 13th power. Yeah, so, wow. You don't think of this as being just this amazingly lucky day where we happen to get this one particular sequence, but it is. Just that one. It was its day in the sun and the wind. Anyways, we can look at sort of the distribution of getting a particular outcome like this with this number of vowels in it by doing what we did up here. And so we're keeping P constant here, but we have to change the binomial coefficient, because instead of selecting just a sequence of 5 C's and V's, we're selecting a sequence of 40. So we can get anywhere from 0 vowels in that sequence to 40 vowels. And I don't know how many vowels we got here. Looks like probably 20 something. Maybe it's easier to count the consonants. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we got 27 vowels out of that guy, for whatever that's worth. Anyways, I can generate a new binomial distribution like that. As you can see, these are all going to be small probabilities for each one of these outcomes. The ones on the tail ends are going to be the just like 0 vowels or 0 consonants, that sort of thing. But we were somewhere in the middle. Like, I think this is our probability. So this is 25, 26, 27. Okay, let's plot it because it's hard to read all those numbers and get any sense out of them. But if we plot this as a bar plot, then, oops, not that, we see something that looks like that. So we can compare that to our first symmetrical plot, which looked like this. We saw this has symmetry. It's, selecting 5 different consonants and vowels, so it's kind of centered between 2 and 3. This one is centered on 20 because we're selecting 40. But you might notice this basically looks like a normal distribution, right? It's not exactly a normal distribution because it has these sort of like staircase effect on the sides, but it's basically that bell curve shape, right? But it's not, what I have to tell you here is that it's not exactly a normal distribution. It just looks very similar to one because it's generated differently mathematically. And the math behind this one is relatively easy to understand because we've done it multiple times already, just using this set of commands right here. Okay, some other fun things you can do with R is to get the particular probability of one outcome with the following command, which is dbinom, for k hits out of n trials where the probability of any hit is p. So for example, if I wanted to look at the probability of getting 0 vowels out of 5 trials in my second setup, where the probability of getting a vowel on any single selection is 1 out of 3, then the probability of that is 0.1316872, or just as a reminder, we decided back here that it should be, blah, 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 32 out of 243, because I'm selecting all constants in that case. And as you can see, that matches up well, so it looks like we did our math correctly. Lucky us. We can also double check, say, what is the probability of getting just 1 vowel out of 5 selections, where the probability of getting a vowel on any individual trial is 1 out of 3. This says 0.3292181, which should be equal to 80 out of 243. And hey, it is. So that's an easy way to calculate those sorts of numbers. We'll plot the overall distribution of this second setup this way. So I'm going to kind of change the overall, or basically crunch out the distribution in a slightly different way. So I'm actually just going to use this dbinom function and spit those numbers out into something called try number 2 here. And we can look at those, and they kind of look similar to what we saw before for that previous plot we made. But here I'll just make a bar plot of try 2. And what do we see? We see the overall distribution being shifted over a bit to the left. And in case that kind of went by a little too quickly, maybe I'll set this up so you can see the switch better. So go up here and plot my distribution for 40 choices as a bar plot. Oopsie, try it that way. And you see it's centered around 20. And if I plot this next one, try number 2, where I just shifted the probability of selecting a vowel down to 1/3, what happens is that it looks exactly the same, more or less, except the whole thing shifts over to the left, so that the center is around like 12 or 13 here, rather than around 20, because it's a lot less likely that I'm going to get a vowel in this case. And we have this longer tail here on the right, which is basically all 0. Okay, that's what's happening when I'm changing the probability of a hit on any given trial here, is that the overall distribution just shifts in that particular direction, closer to 0. All right. I mentioned this, maybe I didn't mention this, but this is a good test. This is, again, a hypothesis test you can use, which is based on this distribution. Like I said, that whole paradigm just kind of still works the same way, except you have to use a slightly different test that is based on this distribution. It's called the Binomial Test. It tests whether a certain proportion of hits on a certain number of trials differs significantly from chance. And this is called the Binomial Test. Sometimes people call it the sign test as well. I feel like this is an underrated hypothesis test, which is easy to use and doesn't involve a huge number of assumptions, so you can kind of apply it in a lot of different cases. For instance, if you are doing like an identification experiment in a speech perception study, and you just want to see are people like actually engaged enough with a task where they're doing better than chance, this is one way you can test that. So for instance, if they're trying to just like identify 5 different vowels in English, and you say, listen to these vowels and tell me which one is which, will they be able to do better than 1 out of 5 on that test? You can use a binomial test to do that. And in R, you can get that to work by using the command binom.test. And so we'll start out by looking at a particular situation where we get only 1 hit out of 10 trials, where the probability of getting a hit is 0.5. So the default probability setting for the binom test is 0.5, which kind of only stands to reason. It's just like flipping a coin, right? And you run it just like this. It's kind of the easiest test to run in R. You just say binom test 1 out of 10, like that. And then it also gives you a nice clear output. Like this is the number of successes, this is the number of trials. The probability of getting that number of successes out of that number of trials is 0.02. And then it also makes it really clear what the alternative hypothesis is here. So it says the true probability of success is not equal to 0.5. And since the p-value is less than 0.05, try not to get those confused, but this is less than the alpha criterion. That means that we reject the null hypothesis and accept the alternative hypothesis, which is that the true probability of success is not equal to 0.5. The one thing that maybe is a little bit confusing here is that this is by default also a two-sided or two-tailed test. So it's just saying it's not equal to 0.5, but it doesn't give you a clearer sense of what that might be. So you can switch that parameter the same way we switched it for t-tests and run it with the alternative equals less setting over here like this. And if I run the same sort of setup that way, you can see my p-value gets cut in half. Before it was 0.02. And now since it's just one-sided and it's the lesser option, I get a p-value of 0.01. So that's still lower than the alpha criterion of 0.05. So I reject the null hypothesis. I accept the alternative hypothesis, which is that the true probability of success is less than 0.5. So before it was just not equal, and now it's saying it's less than. Okay, so I'm flipping a coin. I get heads on 1 out of 10 trials. And based on that, I would conclude that I'm not flipping a fair coin, right? A fair coin should have a probability of coming up heads or tails equally on any given trial. In this case, it looks like I'm getting whatever I consider a success less than half the time. So it looks like this is not a fair coin. We can kind of go back to the Rosencrantz and Guildenstern example by saying, well, he got 0 tails out of 10 trials. So in that case, the p-value gets even smaller. It's much less than 0.05. So yeah, in that case, you definitely say that something's going wrong with that coin or that situation. Right. So I want to make clear here, because this is sort of a situation where you could easily get confused, but there is the sorry about that. There is the probability of getting heads or tails with the coin itself. And then there's the probability based on the binomial distribution of getting that particular number of hits or successes out of a given number of trials. So the p-value here is just reflecting where you are on that binomial distribution, like here, right? Like if I'm out here in the tails, like getting a lot of different hits or a lot of not hits, that is how I'm kind of coming to the conclusion about my hypothesis test. And that is not, this p-value here is not reflecting the probability of getting a success on any given trial of flipping the coin, or any given trial of my experiment, or that sort of thing. Those are two separate probabilities. This is the probability of getting heads when you flip the coin. This is the probability of being on that part of the binomial distribution. So like for this setup, the probability of getting a vowel out of that selection was just 1/3, and that's what the distribution looks like. And if you are way out here, actually we can kind of run that test. Maybe I do. Yeah. So this is out of 40 trials, and I'll give you kind of the 5 trial option here. So the likelihood of picking a vowel on any given trial is 1 out of 3. And let's say I pick 5 tiles out of the bag, I get only 1 vowel. And this is testing whether I should keep this hypothesis that the probability of getting a vowel on any given trial is 1/3. My p-value for that is 0.46, so I don't reject that hypothesis. I keep it and I say, well, this is a likely outcome to get, even though I'm only getting 1 vowel out of 5 trials. That I'll make it more relevant to this particular graph and say, what if we selected 40 different tiles out of the bag, and I got, well, let's make it 8 because you can see that bar right here. Let's say I only got 8 vowels. So, that's the same proportion there, like 1 out of 5. And I should get, well, not exactly. I was going to say I should get the exact same p-value, but I don't. It's basically saying over here, this is far enough away from the mean of this, and with more trials, we kind of get more reliability of our estimates, so that the p-value is less than 0.05. So even though I'm here, which looks like a relatively healthy number, you'd reject the null hypothesis and say, well, the underlying probability of getting a vowel is probably not 1/3, and we have to kind of shift this overall distribution over a little bit to the left to sort of account for the fact that when I actually run the experiment, I'm down here on my distribution. Okay, hopefully that hasn't confused you completely here, but I had to give my best shot because there's 2 different p-values kind of we're playing around with here. Yeah, maybe to make it a little clearer, I can show you what it looks like when we should be somewhere in the middle, which is 12 successes out of 40. There we get a p-value of 0.39, so we'd be at this big bar here at this point. So we're in the middle of the distribution. We say, okay, yeah, we're going to keep the hypothesis that our underlying probability is 1 out of 3. I guess maybe the part that can be confusing is that since we've talked about the math that we use to generate a distribution that looks like this, we understand completely where these numbers are coming from. But remember that when you're running an experiment, you don't know exactly what the underlying parameters are. So let's say you were you're running an experiment where the likelihood of, you had a person selecting 1 out of 3 options. Let's go back to the stop place of articulation example. And you say, listen to this stop. Tell me, is that a P, T, or K? You'd say that, if they're just selecting randomly at chance, they would just select one of those 3 options just randomly on any given trial. And so their likelihood of getting any one correct would be 1 out of 3. But they might be doing better than that, right? So they might be able to identify stops more reliably than 1 out of 3. And so then you'd get, say, maybe more correct answers than just 33% from your subjects. And in that case, you would have this null hypothesis that, they're just monkeys clicking on buttons on the screen and randomly picking one response option. That's your null hypothesis. But then you find out, oh no, they're way over here in the tail. They're doing much better than just random chance. So I reject that null hypothesis that they're just mindless monkeys doing this experiment for credit. And I say, well, the actual probability is probably much higher than 1 out of 3 for these particular subjects. But in that case, I don't know exactly what's going on in their minds, what their exact underlying probability of getting a correct response is, but I just say it's better than chance in that particular case. I've got another example here. I'm glad I kind of threw in that linguistics example because I was too tempted. I couldn't resist to give you another baseball example. So I'll just end with this. But when I was growing up, the standard line in baseball is that if you are a 300 batter, if you got a base hit on 3 out of 10 chances, if you're a 300 batter, you are an excellent hitter, especially in Major League Baseball. The world has changed. It's not how the game works anymore, even though it worked that way for over 100 years. But the question I had here is that what is the probability or likelihood that somebody who gets a base hit on 3 out of 10 chances could go 0 for 5 in a particular baseball game. And I don't know if you've ever played baseball, but you only get a limited number of chances to get a hit in any given game. Like 4 is kind of a default number, 5 is a lot. But sometimes, even though you get that number of chances, you don't get any successes or any hits, so you go 0 for 5. And if we run the binomial test for that, so 0 successes out of 5 chances, where the likelihood on any given trial of success is 0.3, we find out the p-value of that happening is 0.16. So that's not a good enough or low enough p-value to reject that null hypothesis. Our null hypothesis being that this is our underlying probability of success. So we keep that null hypothesis, even though this particular batter on this particular day had a bad day by having no successes at all. It doesn't mean they're a bad hitter, because we can still keep this null hypothesis in place that they meet that criterion for being a good hitter. It just means that due to randomness, sometimes they're going to have a bad day. And that's just the way that life is. It's the way that random chance works in statistics and in baseball and in linguistics too. So in case you're having a bad day, although when the weather's this nice, I don't know why you would, but in case you are, I will say that we'll leave you with this moral of the story, that even if you're good at what you do, you can expect to have a bad day every now and then. Hopefully you're old enough to have that wisdom in place by now, but if you don't, statistics proves it, so don't doubt it. All right, I'm running out of time. I'm running out of voice. I'm running out of water, so I'm going to quit right there, but we're going to talk more about conditional probability when we get back in touch tomorrow. So hopefully it'll be nicer outside and I can record again without the wind ruining everything, but I'll see you guys then.